More than 50 years have passed since the first humans set foot on the moon. They kicked up dust, took photographs, and planted flags. Since then, dozens of missions have returned there. Some landed, others entered orbit, and a few were deliberately crashed to observe what would be ejected from the surface. It is the most visited and most extensively studied celestial body in space after Earth. And yet, despite all of this, we still do not fully understand it. Not how it retains heat, not how it conducts electricity, not even why its soil clings to everything as if it were alive. The deeper we look, the more questions emerge. Some things, like how the moon causes tides in Earth's oceans or triggers solar eclipses, have been understood for a long time. But others, stranger in nature, only became more confusing the closer we studied them. One such mystery began with a signal, a faint chemical trace. Then another appeared, and another. Different missions, different methods, yet all pointed to one unexpected possibility. There was something there that should not have been. What followed was a chain of discoveries, experiments, and contradictions that left scientists puzzled for decades. It is easy to forget how slow science can be. We tend to think that finding something unexpected should instantly change everything, but it doesn't work that way. Sometimes the most important clues are the ones nobody notices at first, or worse, the ones everyone notices but nobody believes. That is exactly what happened in 1976. The Soviet Union sent an automated probe to the moon called Luna 24. It was the final mission of its kind, the last attempt in a long series of lunar soil sample return spacecraft. It did not make headlines. It was neither the first flight, nor the largest, nor the most spectacular project. Yet it quietly accomplished something important. The probe drilled about 2 meters beneath the surface, extracted a small column of lunar soil, and returned it to Earth. The total sample weighed about 170 grams, roughly the mass of a baseball. Not much, but enough for analysis. And inside that narrow tube of dust, something strange appeared, a trace of water. About 0.1% of the sample contained H2O, and the deeper the sample was examined, the more water was detected. This should have been a sensation, but it wasn't. Instead, scientists dismissed the result. They argued that the water likely came from Earth contamination, perhaps from the lander, perhaps from laboratory equipment. It was the simplest explanation. After all, the moon was dry. Everyone knew that. It was written in textbooks, and this was not the first such case. Earlier, during the Apollo missions, samples brought back by astronauts showed similar signs. Not much, only trace amounts of hydrogen-bearing compounds. Some of these may have been hydroxyl, a close chemical relative of water, but even then, they were dismissed as interference, something insignificant. For decades, these signals remained buried in laboratory reports and footnotes. The data was archived. The idea was set aside. No one followed up. No mission was designed to dig deeper or test whether water might actually be real. The assumption that it wasn't persisted. Only in the late 1990s and early 2000s did these early signals begin to look less like contamination and more like overlooked evidence. But by then, years had been lost, ignoring something that had been in plain sight. And when we were finally ready to take a closer look, the moon had already begun to resist. Standing on the rim of certain craters near the lunar poles reveals something almost unnatural. Not because of what is there, but because of what is not. Light, even the faintest glow. Only sharp, permanent shadow, unchanged for billions of years. These regions are called permanently shadowed regions, or PSRs. They exist because the moon has almost no axial tilt. Its axis is nearly perfectly vertical, only about 1.5 degrees off. This means that when sunlight reaches the poles, it grazes the surface at a very shallow angle. And the deeper the crater, the easier it is for sunlight to miss it entirely. So down there are places that have not seen a single ray of sunlight for almost the entire history of the solar system. It is a rare environment, not just cold and unchanging, but completely devoid of sunlight, without warming, without thermal cycles. Temperatures inside some of these regions can drop below -240 degrees Celsius. That is colder than Pluto. In fact, colder than anywhere we have ever measured temperatures, even on the ice giants. These are places where, in theory, ice could survive forever, if it ever got there in the first place. This is exactly what scientists began to consider in the 1990s. Perhaps the moon was not completely dry. Perhaps it simply preserved its water, locked away in these cold traps. And if comets or asteroids carrying water ever struck the lunar surface, and we know they did, some of that material could have migrated into these shadowed basins, frozen solid, and never left again. This idea quickly gained traction, not only because it made thermodynamic sense, but because of what it implied. If there really is ice on the moon, hidden in deep frozen pockets, then it is no longer just a dead rock. It could become a resource, a fuel depot, a place for construction, rather than just observation. Since then, the moon's polar regions have become a new focus of attention. Observing from afar was no longer enough. We had to get closer. We had to look inside. But a problem emerged. These very regions, the most promising ones, are also among the hardest to reach. The terrain is steep and hazardous, the lighting is extreme, and relying on solar power is impossible when the sun never rises. Still, the potential was too important to ignore. If ice truly existed there, it could change everything. One by one, missions were prepared, all with a single goal: find evidence. And that is where things began to get strange again. Once scientists suspected that ice might be hiding in the moon's shadows, the next logical step was to send a spacecraft to verify it. But instead of landing, the first missions chose a safer approach, orbiting the moon and scanning its surface remotely. The first was Clementine, a joint NASA and U.S. Department of Defense mission launched in 1994. Its primary objective was not the search for water, but it still made an important discovery. Clementine mapped a large portion of the moon and found that some craters near the South Pole are in permanent shadow. This strengthened the theory of so-called cold traps. However, Clementine did not carry the necessary instruments to confirm whether anything had actually frozen within them. A few years later, in 1998, NASA launched Lunar Prospector. This time, the search for water was one of the mission's main goals. Using neutron spectroscopy, the spacecraft searched for signs of hydrogen, a potential indicator of water or hydroxyl compounds, by analyzing how particles were reflected from the lunar surface. And it found something. Lunar Prospector detected elevated hydrogen concentrations near both poles, especially in permanently shadowed regions. This was exactly what scientists had hoped for. In theory, it suggested that between 10 and 300 million metric tons of water ice could exist at the lunar poles. This was no longer a small hint. It was a game changer. But there was a catch. Hydrogen alone does not confirm the presence of water. It can also be part of hydroxyl compounds or bound within minerals. The instrument could not distinguish between these possibilities. It only showed that something containing hydrogen was present, not whether it was ice or something else entirely. Even if it was water, orbiters could not see it directly. They could not drill, touch, or scoop it. They could only hint, not confirm. This left the scientific community in a difficult position. The data was there, the hints were strong, but certainty was missing. It seemed as if the moon was beginning to reveal one of its secrets, but still refused to let us get close enough to be sure. Orbiters provided direction, but not answers. The maps lit up with possibilities. The shadows looked promising, but no one could say for certain what was truly hidden within them. At that point, space agencies concluded that a different kind of mission was needed. If orbiters could not reach the ice, perhaps a direct impact could. When orbital missions failed to provide a clear answer, scientists decided to take a more aggressive approach: crash something into the moon and see what gets ejected into space. It sounds crude, but the logic was simple. If ice was hidden in shadowed craters and orbiters could not look inside them, then an impact might excavate that concealed material and expose it to sunlight. Only then could sensors finally determine what was really there. The first serious attempt came from the Lunar Prospector mission. After completing its mapping work, the spacecraft was deliberately directed into a crater near the South Pole in 1999. The expectation was that the impact would produce a plume of debris high enough for ground-based telescopes to analyze and possibly detect water, but nothing came of it. No water was detected, and the experiment yielded no clear results. Some blamed the impact angle, others the instruments. In any case, we learned very little. Almost a decade later, Japan attempted something similar with the Kaguya spacecraft. It had spent over a year orbiting the moon, collecting high-resolution images and topographic data. When its primary mission ended in 2009, it too was deliberately crashed into the lunar surface in hopes that the ejected material might reveal something hidden. Once again, no useful results, no ice, no vapor, just dust. Then came LCROSS, the Lunar Crater Observation and Sensing Satellite, launched by NASA in 2009 with a clear objective: to determine once and for all whether water ice existed in permanently shadowed craters. LCROSS did not hit the moon alone. It carried a companion stage, the spent upper rocket stage, which struck first, crashing into Cabeus crater near the South Pole. Minutes later, LCROSS followed the same trajectory, flying directly through the debris cloud created by the impact. And this time, it worked. Onboard instruments detected water vapor in the plume. Not an assumption, a real, measurable presence of water. Alongside it, other volatile compounds were found: hydrogen, carbon monoxide, ammonia, methane. It was compelling evidence. For the first time, a spacecraft had directly interacted with the lunar surface and confirmed the presence of water ice. The discovery was a sensation. Scientists celebrated. The moon's south pole was officially no longer a theory. It had become a target. But very quickly, new questions emerged. How much ice is actually there? Is it evenly mixed with the soil or concentrated in pockets? Is this ice ancient or relatively recent? And perhaps most importantly, can we use it? The LCROSS mission gave us proof, but it was limited. The spacecraft was destroyed in the process. It could not continue studying, could not extend its observations, and could not determine whether what it saw was typical or just a rare anomaly. We knew water existed, at least in that specific location, but we still did not know how much, how deep it went, or how accessible it truly was. And so newer missions, smarter, slower, more carefully designed, began searching for different answers. For a long time, the idea was simple. If water existed on the moon, it should be found in the coldest and darkest places. Permanently shadowed craters that never see sunlight seemed the most logical candidates. But then something unexpected emerged. Orbiters began detecting faint traces of water molecules outside these cold traps, not deep inside craters, not buried in the soil, but directly on sunlit lunar surfaces. At first, it didn't make sense. NASA's Lunar Reconnaissance Orbiter has been mapping the moon since 2009. Its instruments did more than study topography. They scanned temperatures, measured reflected light, and analyzed chemical signatures. One of its sensors, combined with data from India's Chandrayaan-1 mission, began detecting signs of hydroxyl and water molecules across the lunar surface. Not everywhere and not in large concentrations, but widespread enough to draw serious attention. What was even more puzzling was how this signal changed over time. During the lunar day, especially around noon, when the surface was hottest, the water signatures would weaken or disappear entirely. But as the surface cooled later in the afternoon and into the evening, the signals returned. As if the moon itself were sweating. Water molecules vanished in the heat and reappeared at night, not as puddles or even frost, but as scattered molecules clinging to the surface or possibly moving through the moon's extremely thin exosphere. No one expected this. It is difficult to overstate how unusual it is. The moon has no atmosphere, no pressure to hold water vapor, no weather cycles, no clouds or rain. And yet the data hinted at something resembling a lunar water cycle, not Earth-like and driven by evaporation and condensation, but controlled by solar heating and cooling at a molecular scale. So, where was it coming from? Several theories emerged. One suggests that micrometeorites, tiny cosmic grains constantly bombarding the surface, could deliver small amounts of water or release it from minerals upon impact. Another points to the solar wind. The sun continuously bombards the moon with charged hydrogen particles. When these particles strike oxygen-bearing minerals in the soil, they can form hydroxyl groups. Over time, some of this hydroxyl may transform into actual water. But regardless of the source, one conclusion became clear. The moon was not completely dry, even at the surface. And this once again reshaped the debate. If traces of water exist almost everywhere, perhaps we do not need to build bases only near frozen craters. Perhaps the lunar surface itself is wet enough to harvest resources, if we can figure out how to do it. This realization significantly expanded the map of possibilities. Suddenly, more locations became viable, more landing sites, more opportunities for exploration. This momentum carried into the next wave of missions, landers and rovers designed not only to observe from orbit, but to land, drill, test, and verify everything we thought we already knew. And when one of those missions finally arrived at the moon's south pole, it brought new instruments, new objectives, and a major surprise. In 2023, India launched a mission designed to be different. While many spacecraft had orbited the moon, mapped its surface, or crashed into its craters, Chandrayaan-3 was built to land, and to land in a very specific region. It was headed for the South Pole, an area scientists believed held the highest concentration of frozen water anywhere on the lunar surface. At the time, the logic seemed solid. Several missions had detected hydrogen signatures. L-Cross had confirmed water vapor in a shadowed crater. Temperature data indicated conditions cold enough to preserve ice. Everything pointed to a coherent picture. All that remained was to send a spacecraft and look closer. Chandrayaan-3 arrived in July. The lander, named Vikram, successfully touched down on the surface, making India the fourth country to land on the moon and the first to do so near its south pole. Inside it was a small rover, Pragyan, equipped with instruments specifically designed to analyze lunar soil and confirm what decades of missions had suggested, that water ice was there, but it wasn't there. The rover moved slowly across the surface, scanning the lunar regolith with two separate instruments. One used lasers to vaporize tiny patches of material and analyze its chemical composition. The other fired alpha particles and X-rays to achieve the same goal through a different method. These weren't assumptions or indirect hints. They were direct in situ measurements, the kind of hard data scientists had been waiting for years. And yet, when the results came back, they were unexpected. The instruments detected aluminum. They found iron, calcium, chromium, sulfur, even titanium. All of this was valuable for understanding the moon's geology and history. But one key element was missing: hydrogen. And without hydrogen, there is no water. The rover examined multiple locations. It stopped near craters. It analyzed untouched soil. But the outcome remained the same. No water ice, no hydroxyl signals, nothing that matched the traces previously suggested by orbital missions. This absence made little sense. This region was supposed to be one of the most promising wet zones on the moon. So why was it dry? Had something changed? Were earlier measurements wrong, or was the water simply deeper than the rover could reach? There was no clear answer. The mission continued gathering other data, measuring temperature and testing the lander's ability to perform short hops across the surface. But when lunar night arrived, both the lander and rover shut down. They were not designed to survive the extreme -14-day lunar night cycle. After that, they never woke again. Chandrayaan-3 still delivered valuable science. It proved India could land near the lunar South Pole, mapped new surface features, measured terrain properties, and recorded heat flow. But it did not solve the water mystery. It complicated it. If water was supposed to be there and all the maps, models, and measurements suggested it should be, then why couldn't we find it? Attention slowly shifted back to something previously overlooked: the soil itself. Maybe the ice was there all along, just not accessible at the surface. It is easy to imagine the moon as a simple, lifeless gray landscape shaped only by dust and rock. But Chandrayaan-3 quietly revealed something more subtle, not by what it found, but by what it felt. The Vikram lander carried the CHASTE instrument, Chandra's surface thermophysical experiment, designed to measure how heat moves through lunar soil. A probe was inserted gradually, centimeter by centimeter, recording temperature at different depths. At the surface, it was about plus 60 degrees Celsius, expected under direct sunlight. But just 8 centimeters below, temperatures dropped to around minus 10 degrees Celsius. A dramatic difference over such a short distance revealed something important. Lunar regolith is an excellent insulator. Heat does not travel easily downward, meaning subsurface regions can remain cold enough to preserve water ice. This was not a model or assumption. It was direct observation. The upper layer of dust acts like a thermal blanket, protecting what lies beneath. If water exists just a little deeper than the rover's instruments could reach, surface scans would miss it, while orbital data might still detect indirect signatures. That would explain the mismatch. The ice might simply be deeper than we can currently drill. This idea aligns with earlier findings. Apollo and Luna missions had already hinted that water content may increase with depth. Orbital spectrometers detected signals that could not be explained by surface chemistry alone. Even impact ejecta suggested subsurface volatiles were present, lifted from below. Perhaps the truth was simple. The moon is not dry. It is just layered. Ice may lie beneath only a few centimeters of insulating dust, invisible to shallow instruments. The limitation was not the moon, but our reach. The next lander would not need better cameras. It would need a deeper drill. For decades, lunar water was mainly a scientific curiosity, useful for understanding the moon's history and the evolution of the solar system. Today, it represents something far more practical: independence. If usable water exists, long-duration missions become possible without hauling supplies from Earth, where every kilogram costs thousands of dollars. It can support drinking, food production, cooling systems, and life support. Water can also be split into hydrogen and oxygen, essential rocket propellants. With lunar extraction systems in place, the moon could become a refueling hub for missions heading to Mars, asteroids, and beyond. That changes everything. Launches from the moon require far less energy due to its weaker gravity, only 1/6 of Earth's. Local water also supports closed-loop life support systems and even future agricultural experiments. And finally, there is a geopolitical dimension. Control over lunar resources brings strategic advantage. Countries are not competing for the moon just for the scenery. Here, water is infrastructure. The first nation or private entity to secure reliable access to usable lunar water will gain far more than prestige. They will gain leverage over access routes, logistics, and ultimately the architecture of future space exploration. That is why the lunar South Pole is becoming increasingly crowded, and why missions keep circling the same promising regions. And it is also why every hint that ice might be there, and usable, raises the stakes. This is no longer about curiosity, it is about capability. Yet even with this growing interest, one fact remains clear: we still do not know how much water is actually available or how difficult it will be to extract. Because everything depends on it: fuel production, lunar bases, deep space missions. And it only works if water can be reliably accessed. This leads to the core problem. Despite decades of missions, data, and optimism, we still do not have a complete picture. Every time the moon seems understood, it introduces new contradictions, conflicting measurements, missing signatures, unexpected results. The pattern repeats again and again. We have seen strong hydrogen signals from orbit, yet landers often fail to detect water in the soil. We have observed traces of water vapor in impact plumes, but not the expected frost, ice sheets, or visible deposits. Even in permanently shadowed craters, places that should have preserved ice for billions of years, high-resolution imaging has yet to reveal anything that clearly resembles large ice bodies. Instead, we are left with ambiguity. Shallow probes return dry readings. Instruments detect water that appears to vanish during the lunar day. Rovers traverse craters believed to contain frozen reservoirs and find only dust. Even newer systems, such as ShadowCam, designed to peer into the darkest regions of the moon, have not yet confirmed the expected reflective signatures of ice. This raises an uncomfortable question. What if our understanding of how the moon stores water is fundamentally wrong? Perhaps the models need revision, or worse, the water is there, but so finely dispersed, so deeply buried, or so chemically bound to minerals that we are not yet equipped to extract it. It is also possible that our instruments, despite their precision, are still not sufficient. Orbiters cannot drill. Landers carry only shallow penetrators. Spectrometers detect indirect reflections rather than direct samples. And even then, interpretation is difficult. Hydrogen does not always mean water, and brightness does not always indicate ice. Yet despite all this uncertainty, interest in the moon is only growing. More missions are being planned, more landers are under development, and the South Pole remains the primary target. The underlying assumption persists. Something valuable is there. We just have not reached it yet. Perhaps the next mission will carry better tools, a deeper drill, or a functional extraction system. Perhaps it will finally bring up something cold and solid from beneath the unseen threshold, or perhaps it will simply add another anomaly to the list, another reminder that the moon does not easily give up its secrets. But one thing is certain: whatever the moon is hiding will not remain hidden forever. We have already come too far and looked too closely. And if we do find what we are searching for, not just molecules or faint traces, but real, usable water, it will mark the beginning of something far larger than the moon itself. Because the moment we stop relying entirely on Earth is the moment the rest of the cosmos truly opens to us.